So we've got this paradox that we'd like everybody to measure the same speed of light, even if they're moving. So if I'm running along here, I should measure the speed of light, but you looking at me should also measure the same speed of light from me. And that's weird. And so we're going to have to do some violence to common sense to make this to work. Now we've had this transform, the common sense transform, the Galilean transform, and that says that if I'm going fast and I throw something forward, that thing should be going even faster, the velocity should add. So we're going to need to do some violence to that. There are various possibilities we could do. We could, for example, change lengths. So if I'm running forward and I throw something, to me it's got to go at one speed and it's got to be at a different speed for you. So maybe it's because time speeds up or slows down for me, or maybe the lengths change.
So I bet you mathematically, we sit down and do some algebra, we can calculate a transform in which the speed of light is the same for everyone, but it's going to mess other things up that we hold to be true, I think.
Yes, we're in a tough situation. I mean, the transform we just talked about is so common sense. Velocities adding up, positions adding up. It's just saying that your time is my time.
Yep.
That's what common sense tells us. But if we're going to make this work, we need to come up with a transform that does violence to that in order to keep the speed of light sacred.
Well, desperate time calls for desperate measures, so let's figure out what happens if we keep the speed of light constant for everyone.
So it turns out that if you want the speed of light to be constant for everybody at every time, there's only one set of transforms that can do it. And this is worked out by Lorentz just before Einstein got there independently a year later. And these are them. So here's our common sense transform, which tells us that in my frame reference, it's just your frame reference plus velocity times time. But Lorentz said it's the same thing, x prime equals x plus vt, but there's a constant gamma in front. What's gamma? Gamma is this rather weird thing down here. So it's 1 over 1 minus root v squared over c squared. So v is velocity, c is the speed of light. If the velocity is much less than the speed of light, that's going to be a very small number. Squared is even smaller. 1 minus it's going to be about 1. So it's approximately 1 over root 1, which is 1 over 1, which is 1.
Right.
So what that means is for slow speeds, this equation and that equation are pretty much the same.
Right, because we have that is 1, so yeah, for slow speeds it's just x plus vt, exactly what we had.
And that's a good feature of this relativity theory, that it behaves like good old Galileo stuff when speeds are low. It doesn't disprove, you're not going to fall off your bicycle because the new theories come up. It behaves like the old ones, and that was necessary. For z, there's no change. Time, it's a bit weirder still. Once again, when you make the velocity very low, this comes out as the same as that. But what you're seeing here is, once again, a gamma plus a velocity times the position over c squared. So this actually depends on where you are as well as the time. So that's a bit weird.
Okay.
What's this gamma? Here's what gamma looks like. I've plotted gamma against velocity as a function of the speed of light. And what you can see is when you're going much less than the speed of light, it's pretty much down 1.
So even at 40% of the speed of light, it's almost 1. But when you get up to...
Yeah, and our fastest spacecraft are about here on the scale, about 2 pixels in. So
99.9% of the speed of light, then this number starts becoming really weird, like bigger than 5.
And it starts heading off to infinity as you start going to asymptotically up to 1. When you get v equals c, that's 1 over 1 squared, which is 1, so 1 minus 1, which is 0, 1 over root 0, which is infinity.
So that means as I start going closer and closer to the speed of light, our relative velocities are, this number is going to become much bigger than 1, which means it's going to be like the distance between us is more than just this x plus vt. It's got this extra factor in it.
Yeah, so if you're sitting there with a ruler, you think your ruler is a metre long, but I won't. I'll get a different length for it. And also your time, your clock, you might think an hour has passed, and I think a different amount of time has passed. And even worse than that, let's say you have 2 clocks at different ends of your boat, they'll have different times according to me because they've got different x coordinates.
Ooh, okay, so that's really going to break some of the things that I think we think as being just part of nature around us, right?
Yeah.
It means
so we've got 3 real problems here, and if you do the sums, you find the first effect is time dilation. If you race past me, for your point of view, nothing's changed.
Yep.
Your clock's running at normal time, yeah, it's going fine. Your rulers are all the right length, the speed of light in all directions is the same for you. But when I look at you, to me, you seem to be going really slowly.
So if you're looking at my clock,
yeah,
it's like it's slowed down as I go away from you.
And you seem to be talking very slowly.
Yeah, okay.
But then curious enough, from your frame reference, you see the same for me. For me, I think I'm fine, but you look at me and I would appear to be going really slowly and my clock would be moving. But to me, I look perfectly fine.
Okay, and what about this link? We saw that links are messed up as well.
Yeah, so to me, if your length in the z coordinate looks normal, so you're
Yes.
as high as you ever were,
But I'm
you're
not
much
moving
thinner.
that direction, yes?
If you're moving this way, you're much thinner. So you seem to shrink along the direction of your motion. But from your point of view, you look perfectly normal.
Not completely normal, but you look shrunk as well.
Yes.
Ah.
And possibly even the worst thing is simultaneity, that things appear, if you look at this equation back here, you see that two things that happen at the same time from your frame of reference, if they're at different x-coordinates, will appear at different times from me. So let's say, for example, you did open both your hands simultaneously. Because they're at different x-coordinates, I will think you opened one of them before the other. So
Or in other words, if I drop a ball out of two hands, when I drop them, of course, from my point of view, those balls are going to hit the ground at the same time.
from my point of view, you'll drop them at different times and hit the ground at different times.
Right. Ooh. That means things happen at different times depending on where you are and how fast you're moving relative to what's going on.
And even in different orders. So, for example, if you're going this way, from my point of view, you'll drop this one first and then that one. But then if someone going the other way, it might appear you're dropping the opposite way around. So it's making cause and effect different. What happened first?
That's pretty deeply disturbing.
It is indeed. So these are the three weirdnesses: time dilation, length contraction, simultaneously removing. But they do solve the problem of light. So the idea is, let's say you're trying to measure the speed of light. So let's say you're driving along your barge and you've got a torch in your hand and you turn it on at some point. And when you turn it on, there's an event here, it turns on, and a bit later there'll be a second event over here when it's picked up by the receiver.
Right.
So you've got event 1, event 2, and in your frame of reference you'd measure when event 1 happened, when you turned the light on, when event 2 happened. You'd take the difference in time, the difference in distance, divide one by the other, and work out the speed of light. From my point of view, I'd use the Lorentz Transform. I'd measure when the first event happened and convert it from your x, y, z, and t to my x prime, y prime, z prime, and t prime. And I'd convert the second event using those equations. And it turns out that if you do that, I will measure the same speed of light as you did. So
At least we will get what we seem to see in nature,
Yeah.
at least, so that would be good.
from my point of view, you are doing the experiment really slowly, and your experiment is shrunk.
Yep.
Both of which are going to change the answer. It turns that those two effects just happen to cancel out and give the same speed of light.
Okay.
Now, this is a bit complicated, so what we're doing is we'll just take it from, you can either take it from trust to us that these things will work, but I'll also put in an appendix a calculation where I show that the Lorentz transform actually does give you the same speed of light, and I will show how it changes time and changes length. If you don't want to do the maths, don't worry, you don't need it for the exam, and just feel free to skip over to the next thing. But if we do muck up the transform to explain this constancy of the speed of light, this is the price you pay for it.
Very profound things that should happen in nature. And of course, the best thing to do is to go out and test these things to make sure that they really do happen in nature. Or else we know that it's an interesting idea, but it's wrong.
I'll have to find some other way out of the paradox.